That is very loud. Will that do? Okay. Let's go. strong interaction. Mesons. Try this. SU3. Oh, QQ interaction. Quantum chromodynamics. Wow. Exclusive to SU3. Transform the colors. Okay, so quantum electrodynamics says that it's an interaction between two electrons, actually a positron and an electron, putting it together, make it into a very excited photon. Whoopsie, it's supposed to look like this. Wah, 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 wiggly. Excited photon. A single. This doesn't exist, by the way, but it's a very good analogy. I'll just write it down. Not exist. Not a reaction, I mean. Not a real reaction. Okay. Then it's a vertex. But in QCD, however, it's going to be the interaction between two quarks. Let's see. Q and Q interaction. And then instead of a wiggly, it's going to be a spring-looking thing. And instead of a photon, it's going to be a gluon. That's the one that binds the quarks together. There's 8 of them, by the way. Okay, so there's 8 of them. Okay, so that's where it came from. Those are the 8 gluons that we're trying to find, which is represented as a matrix right here. The Gell-Mann gluons. Okay, now that makes sense. Oh wait, I kind of made a mistake right here. It's supposed to be a 1. Ba-ba-ba. There you go. Yeah, that seems about right. Good. Everything is well. Very nice. Okay. And I'm still iffy about this one right here. These two are supposed to be this combination of this lambda 8. I need to read up on this. So there's a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. These two do not exist by themselves, but only on the amalgamation of them combining into this. I don't know why, but I need to take a look at that. Let's see. So the gluon of 8, got that? Just single QED. QCD and QED. Okay. Very good. Gluons are massless like photons, but strong force is short range. So instead of electromagnetism, it'll be strong force. And it will be short range. Unlike electromagnetism, it'll be long range. Gluons have color charges. So instead of thinking of actual charges for electrons, protons, electrons, positrons, electron, positrons, protons, etc. of the like, we're thinking of color charges for quarks. There's the one, yeah. So photons don't have electric charge. Yeah, that's true. So gluons can interact with each other, exert strong force. Okay. Why don't quarks exist by themselves? I'm not sure. Let's see. Oh, those are the list of 4 questions. Okay. Listing the issues. Gluons are massless like photons, but strong force is short range. Gluons have color charge. Photons don't have electric charge, so gluons can interact with each other, exert strong force. Why don't quarks exist by themselves, and how do quarks interact? Cool. So the 4 issues that we need to take a look at. So should be. Let me take a look at the 8 colors that I needed. Let's check it out. Eight color charges. Yes, the red, green, blue. Those are just names. It's not literally red, green, and blue, but those are just names. It's just like spins. It's not actually spins, but it's up and down. We just like the naming. Let's check it out. Color charge. Right there. Yeah. Let's represent as circles with the color charge in the center and the anti-color charge on the outside. Hadron with 3 quarks. Oh, of course, that thing. Yeah. Nice. And it's going to be supercharged. Nice. And that's the end of the article? What? Come on. I'll just show his screen. What? Whoops. Am I still streaming? Yep, that's good. Let me do it like this. YouTube chat, Krita, and display capture. Here it is. you go. Let's check it out. Ah, here's that's what we needed. Quark and anti-quark attract. Okay. Oh man. Okay, color interactions. So we need to go back here. I'll just state the issues. Okay. And I don't have electric charge. Lambda. Sorry, gamma. Gamma. Actually, a photon. So gluons can interact with each other, exert strong force. Why don't quarks exist by themselves? Question. Yeah, that's a strange phenomena. Exist by themselves. They seem to have a half-life, very small half-life when they exist by themselves. They decay very easily. So why is that? How do quarks interact? Recall at U1. We get exchange photons. Now on SU3. Eight gluons now. Up quark, down quark, and time goes that way. Gluon has color charges. Has 8 color charges. Gluons has color charge. 8 different gluons. Quark-anti-quark interaction. Okay, I need to look this up. Why aren't there? Why aren't there 9 color charges? Why are there only 8 gluons? Variations. You might think that every color-anti-color combination that you can dream up of be allowed, giving us 9, but our physical universe plays by different rules. Here's the incredible and surprising physics of why we only have 8 gluons. Okay. Oh yeah, I remember this. It could be any one of these. With an addition. Mass and energy, which is also attractive. There's no upper limit to how much mass energy you can have, as the worst you can do is create a black hole, which still fits into the theory of gravity. Every quantum of energy, whether it has a rest mass, like an electron, or not, like a photon, curves the fabric of space, causing a phenomena we perceive as gravitation. Okay. Hold on. Let me see if, Whoa, no, not that. Forbes. Here. Ethan Siegel. I like your mustache. And beard. I like it. Okay. Seems favorable. Seems reliable, I mean. Graviton requires to carry the gravitational force. Electromagnetism. There are only a few fundamental forces, each governed by their own rules. Gravitation, there is only one kind of charge, mass/energy, which is always attractive. There's no upper limit to how much mass is needed. Let's create a black hole, which still fits into every quantum of energy, whether it has a rest mass like an electron or like a photon, curves the fabric of space, causing the phenomena we perceive as gravitation. If gravitation turns out to be quantum in nature, there's only one quantum particle, the graviton, requires to carry the gravitational force. Ooh. Okay. I remember that. Electromagnetism, yeah, big one. The other fundamental force, reality appears to microscopic scales, gives us a little more variety. Instead of a type of charges, there are two positive and negative charge. Like charges repel, oppose, charge attract. Although the physics underlying magnetism is very different in detail than the physics underlying gravitation, its structure is still straightforward in the same way that gravitation is. You can have free charges of any magnitude with no restrictions, and there's only one particle required, the photon, to mediate all the possible electromagnetic interactions. There's only one particle. Okay. Rules become fundamentally different. To look up the strong nuclear force. Okay. Instead of one type of charge, or even two, there are three fundamental charges for the strong nuclear force, known as colors. In addition, colors obey different rules than the other forces. They include the following. You cannot have a net charge of any type. Only colorless states are allowed. The color plus its anticolor is colorless. Additionally, all three unique colors or anticolors added together is colors. Huh. Okay. It's like saying it's neutral for charges, if I'm getting that analogy correctly. Color charge of one color. Each antiquark has an anticolor assigned to it. Each quark contains a net color charge of one. Okay, each quark contains a net color charge of one color. Each antiquark has an anticolor assigned to it. Okay, cool. The only other standard model particle with a color is the gluon. The only other standard model particle with a color is the gluon. Quarks exchange gluons, and that's how they form the bound states. 1980, 1990. It's very good. Although these are some complicated rules that are very different from the rules of gravitation and electromagnetism, they actually help us understand how individual particles like photons and neutrons are held together. Okay, I need to write this down. Colors obey different rules than the other colors. They include the following. What do these three associate with then? Okay, these are quarks right here. And these are the bosons? Is that it? Z, W, and there's probably a third one. Boson. Oh well, I'll see what happens. I'll focus on poly later on. Right now, let's do Jailman QCD. Oops. Rules. Rule the rule the. Wait, should I put it right here or? Yeah, it's fine right here. Rules for color. You cannot have a net charge of any type, only colorless. Only colorless states are allowed. A color plus its anticolor is colorless. Additionally, all three unique colors or anticolors added together is colorless. It's like saying it's neutral for a charge, for charges, maybe? Well, probably, most likely. Additionally, all three unique colors, or anticolors, added together is colorless. All three unique colors. Is colorless. Okay. Each quark contains a net color charge of one color. Each antiquark has an anticolor assigned to it. Each quark contains a net color charge of one color. Net color charge of one color. Each antiquark has an anticolor assigned to it. is an anti-color assigned. The only other standard model particle with a color is the gluon. Okay. Standard model particle with a color is the gluon. Quarks exchange gluons, and that's how they form bound states. Oh, okay. Let's see. Was for color charges. You cannot have a net charge of any type. Only colorless states are allowed. A color plus an anti-color is colorless. Additionally, all three unique colors or anti-colors added together is colorless. Okay. Each quark contains a net color charge of one color. Each anti-quark has an anti-quark assigned to it. Anti-quark. Whoops. I might do this. Each anti-quark has an anti-color assigned to it. Yeah. Whoops. Anti-color. Assigned to it. The only other standard model particle with the color is a gluon. Okay. Quarks exchange gluons, and that's how they form bound states. Let's take a further reading. Oops, crap. First off, protons and neutrons themselves and other particles like them, called baryons, must be composed of 3 quarks. Okay, always 3 quarks, each possessing a different color. For every particle, like a proton or neutron, there is an antiparticle counterpart made up of 3 antiquarks. Okay. For every particle, like a proton or neutron, there's an antiparticle counterpart. Antiparticle made up of 3 antiquarks. Okay, cool. Each of which contains a different anticolor. Every combination that exists at every moment in time must be colorless. The combination exists colorless. Which means 1 red, 1 green, and 1 blue color for the quarks. 1 cyan, anti-red, magenta, anti-green, and yellow, anti-blue, anticolors for antiquarks. Okay, like all particles governed by a quantum field theory, the way that the strong nuclear force works is through the exchange of particles. Unlike gravitation or electromagnetism, however, the structure of the theory behind the strong nuclear force is a bit more complicated. Okay, then tell me. Whereas gravitation itself doesn't change the mass energy of the particle involved, and electromagnetism doesn't change the electric charge of the particle attraction of powers of one another. The color, or anticolors of quarks, change every time the strong nuclear force occurs. Okay. Every time a strong nuclear force occurs. Yeah. Charge or particle attraction. The colors, anticolors of the quarks, change every time the strong nuclear force occurs. I just put the colors, okay, of the quarks change every time the strong nuclear force occurs. Colors. of the quarks. Antiquarks. Change as the what? As oh, every time. Change every time the strong nuclear force occurs. Change every time the strong nuclear force occurs. The way we visualize. Oh, yeah, like that. Oh. That's cool. The way we visualize this is through the exchange of gluons. Every gluon will be emitted by one quark or antiquark. Ouch. And absorbed by another quark or antiquark, which is the same rule that the electromagnetism follows. Every photon is emitted by one charged particle and absorbed by another. The photon is the force-carrying particle that mediates the electromagnetic force. The gluons are the particles that mediates the strong nuclear force. Yes, very good. Okay. You might imagine right away that there are 9 gluons that are possible. Okay, here it is. One for each of the color-anticolor combination possible. Indeed, this is what most everyone expects, following some very straightforward logic. There are 3 possible colors, 3 possible anticolors, and each possible color-anticolor combination represents some gluons. If you visualize what was happening inside the proton as follows. A quark emits a gluon, changing its color. And that gluon is then absorbed by another quark, changing its color. You get an excellent picture of what? Absorbed by another quark and changing its color. Get an excellent picture of what is happening with 6 of the possible gluons. Okay, cool. Up, down, up. So you have 1, 2, 3, 4, 5, 6. One red, one green, and one blue, summing up the colors. And it's pretty clear that the following 6 gluons exchange good color. Following 6, huh? Okay. Red quark could emit a red anti-blue gluon, turning it blue and turning the blue quark red. Or a red anti-green. Red anti-green. Where are you? Oh, turning the green quark red. Or the blue quark. What about the other ones? After all, what did you expect? Red anti-red, green anti-green, and a blue anti-blue gluon as well? 6, 7, 8. It'll be a red anti-red, green anti-green, and blue anti-blue glue on as well. Okay. Fortunately, no. Let's say you did. Let's say you had a red anti-red glue on. A red quark would emit it, remains red. But which quark is going to absorb it? Green quark. Do that because there isn't an anti-green part to cancel it out and turn it to colorless, so it can pick up the red from the gluon. Similarly, the blue quark can't because there are no anti-blue at the gluon. Does that mean there are only 6 gluons and the other red can physically exist? Not quite. But you can't have pure anti-red or green anti-green. Mixed state. That's a part red anti-red, part green anti-green, and even part blue anti-blue. Ooh, okay. So that's why. It's because in quantum physics, particles or particle combinations with the same quantum state all mixed together, it's unavoidable. Yes. Up, anti-up, and down, anti-down quarks. The other allowable gluons are combined of red, anti-red, red, green, anti-green, and blue, anti-blue. Okay, let me see. So you have, okay, so this one has a probability between the 3. Okay, wow, that's amazing. So these 2 won't work. Okay. There aren't 3 of them either. The key reason. Okay, why are there not 3 of them? 3 of them either. The key reason is this: because of the specific properties of the strong force. There's one more constraint. Whatever you have as a color anti-color combination for the single color, you need a negative color anti-color combination of a different color. Okay, let me read that again. Color anti-color combination for a single color. A different color in order to have a real gluon. Let's show you what this looks like with an example. Say you want a gluon that has both red, anti-red, and blue, anti-blue properties. The actual color choice themselves are arbitrary. You can do that, but the combination you'll need is... Okay, I remember this one. Yeah. It's a probability of being this, or probability of being that. Which has a negative sign in there. Now you want another gluon, but it has to be independent of the combination you're going to use. That's okay. We can write one down. It looks like this. If you write one, wait, hold on. It has to be independent of the combination you already used. Is there a third combination we can write down that's independent of both of these combinations? Independent, huh? What rules we just talked about? You could write down a third gluon of the following form. 12. 1, 2, 3, 4, 5, 6, 7, 8. Huh. 12 and then 24. Okay. Oh man, I have to go. Huh. I have to go tutor someone. Peace.